is Twitch Studio Beta. I didn't know that something like that existed. And I'm gonna be changing some of these kind of colors and whatnot. And there's even like a right away set up a be right back screen, which is pretty cool. Okay, but I see the microphone is still, but I can mute myself. And then there's like a chatting one where I'm a bit bigger in there. That's pretty cool. I mean, you can do that with OBS as well, obviously. But this is all nicely integrated with Twitch. Yeah, seems to work. Seems like at least the Twitch app is telling me that I'm live, which is good. And yeah, what are we gonna do? This week's schedule is gonna be a bit messed up, just because we have some I have some kind of like personal stuff that needs to be taken care of tomorrow, today as well. So it's gonna be a bit weird. I think I'm not gonna do a full hour. We'll see. But I want to kind of keep banging my head against this thing here. And I realized I said something really stupid last time, which is that I was complaining about these, and I was like, well, that's the point, right? That's not the point. The point is like if you have something like these, uh, because what I was doing 0, 1, yeah. So I was doing all these, and then I was saying, okay, so how would this work, right? So you can. What about the CPU here? It looks like a bit slow as well on my end. 27%, 19%. We'll see. It's good. OBS is performing quite well. Cool. So, and I can see here in the chat. That's cool. Okay. So, and I was saying, okay, so I can just kind of like abstract the zero away or like factor the zero out, and then what do I do with the rest? And I was like, well, it's not, you don't do anything with the rest. You just you just kind of have like uh, so what you would end up with is you would have one zeroth node that is connected to all the other hyper edges, and so you're gonna have it's gonna be part of 4 hyper edges, and uh, and then kind of the next step is like you'd say, okay, so for this node, do I have because I think what I was doing last time was wrong. I maybe I might have been just too quick to say that the just doing sort of doing the factoring is wrong, is something that I don't want to do or something. Maybe that's just the way. It's just I was doing this wrong before. Because before what I was doing is like saying, okay, so the algorithm was naive because it was implemented with with just 2 nodes in mind, hypernodes. And then I was like, okay, so for 3, it's the same. It's just the same algorithm just scaled with 3. So the problem with that was that, yeah, then you kind of have the situation where you can end up, if you do it like this, give me a second. There you go. If you do this like by pairs, right, and say, okay, so this 0 is equal here as well, so we're just gonna move it away from here. Um, you might as well just pick like this one wrongly, which kind of then, if you ignoring these and then you take the other one, that would lead you with, say, a 0 and then a you can have a 0, 1, and then you have a 0, 0, so that'll be one branch. And then you might pick up, so I pick up these and these, and then I pick up this one and this one, so you end up with like a 0, and then a 0 and a 1, and then a 1 and a 1. And okay, but you can still merge these two, right? Because now they're the same. No, that's not true, because they're because you can't really merge them. Exactly, I remember that. So I was just taking them. I think that was just wrong. I was taking the things out, and I should just keep them in the hyper edge. I can have, yeah, exactly. But I still I can do pairs, right? Still I can do pairs and say, well, look, now this is equal, so I can also just keep that. This is equal, right? And then in this case, we just have, well, it's a 0 and it's a 1, and then we just like a 0 plus 1, right? So yeah, yeah. It's the I just don't want to. I want to think about this twice before I start coding these, because last time I realized, but it shouldn't have just given up. That's the problem. And I don't know if I should just do things from scratch, or I think I'll just probably do things from scratch. It'll be beneficial anyway, because you know my 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 other alternative is that I kind of try to keep banging my head against, and the idea of uh, finding a way finding a way just for me to find a way to transform a hypergraph that is already fully factored out into another one that's fully factored out directly, without doing this kind of like unfolding step. And the problem is in the way the gates must be specified, because gates are specified at the system level. That is kind of the main. But this is sort of, maybe I should spend a bit more time on this, because this would be cool. This would just be cool. Let me just get rid of these, um, and kind of like do again what I was doing here. I don't remember. So let's kind of take the case of the CCX, right? Because it's an easy. And let's do some examples, because this is an easy enough gate, because it actually has the definition where I know that I just need to replace. I just need like two rules, two match and replace rules. Because the rest stays the same. But that's the essence of the problem. The essence of the problem is that uh, I'm being forced to match at a system level, and so yeah, that's what sucks. I'm being forced to match at the system level, and this means I'm in a way I will always be forced to actually transform the system at a, like the qubit level system. I'm not using standard terminology. I'm just, when I say qubit level, what I mean is like from the qubits perspective, just not at the system level, but like just with the subsystems in mind. So the states of the separate qubits and their entanglements or their correlations. I'm forced to transform these to the full system view so I can do the match replace, and that is the main issue, right? So that's why I was looking for that's why I'm looking for a way to represent an operation just by talking about the subsystems and not about the system, right? And that's easy to do if the gate is not entangling, because this means that the gate can be broken down, right? So if gate is not entangling, it can be blah, broken down to qubit level operations, right? Which means that I just, you know, I can eventually compress all these and then say if, just if this is this, then replace, right? Um, yeah, you still have to. Actually an easy example would be the sort of a Hadamard layer, right? Which we often like write as just one box, right? But it essentially is just a Hadamard in every qubit. So if I have a system that is in the state 0 plus 1, 0, 1, you have like 3 qubits, right? And I apply a Hadamard layer. What I'm actually saying is apply Hadamard to each one, right? So this Hadamard layer, which is basically consist of two rules, right? The rule would be find a 0, replace it by 0 plus 1, find a 1, replace it by a 0 minus 1. And so, for these cases, it's easy. And in the case above, what we would do is we would just kind of split the nodes, right? I think that's the, yeah. So we'd split the nodes and then apply these, and then we'll need to do this kind of like solving for interference, right? So I think, so you have multiple nodes and you got to keep solving for interference. That's why these make sense, yeah, in a way, right? So in the case of 0 plus 1, then you would basically first break into like a 0 and a 1, and then you would do 0 plus 1, 0 minus 1 kind of thing, and then you would solve for interference, and then you would, what am I doing? And then you end up with with a 0. But it's two simple rules, right? Now 2-qubit, so controlled operations are easy to do as well, because two-qubit operations, no, controlled operations are always easy to do, right? Because you kind of have this rule, if like you have this rule, right, of say if if you okay, so actually look at this. So the way to approach this is by being able to nest rules, right? Because the splitting happens always. So 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 if it's just one rule, if the control is one, then what you're basically doing is you're nesting the rules. So then you're saying uh, huh, ho, 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 ho. 'Cause I'm thinking now. Uh, I don't know if I'm glossing a bit something too much because here I would say this expansion also should happen if you have more qubits, right? Well, no, because again, there's no hyperedge, right? Because there's no correlation, or there's just one hyperedge. Oh, damn it! Need to drink something. So, and so there's a one, then it's a bit of it's a bit of a special rule, right? So if there's a one, you're replacing another one. So okay, so that is that is the difference, right? So these are sort of local replacements, and I'm probably abusing language here, um, just because it doesn't mean they are local necessarily, but it's just one qubit, and so these are um, in these are non-local replacements in the sense that local it's a local match replace. And it's a non-local match replace, which means that I'm matching in one qubit, but I'm replacing another qubit. So so match for q0, and then and then what you're doing is you're saying run some local match replay. So you're saying run these, right? Um, obviously. So that's how you would specify the rule for the control node. So yeah. So this expansion like does not generate new hyperedges, but these does generate new hyperedges. This does generate new hyperedges even only if the actual replacements lead to a different value of the second qubit in this case, right? Because where I'm going now is that I think maybe the trick is if every n qubit operation in general can be broken down into a universal gate set, which is just like the Hadamard and the control node, for example, right? Then that should be then that should be what I do. Then that should be, I think, the key. That is, I think that should be the key. Maybe that should help me get like a more compact representation in terms of rules. Um, yeah, because that's the point. It's the same with matrices, right? Like if you have like a 5 qubit operation, you can, yeah, sure, you can do like a 5 by 5 matrix, but you can also break it down into smaller matrices, which then turn into a tensor network, which, well, it's easy because you have a bunch of smaller matrices that they kind of connect to each other, and then you can do some kind of tensor um, tensor network magic, and then you get some, a bit more efficient simulation. So I think that's, in this case, the same idea. It's like break a CC knot. Like, what is the? See if I can open Chrome and the thing doesn't explode. I'm getting a better machine soon. That is also good. Obviously, we're gonna go incognito and close this one. And so, what about the CCX decomposition? Because we could start with this one for today's stream. Ich stimme zu. I should just probably go to pictures. What is this? Bid. Yeah, there you go. There you go. Something like this, yeah? Yeah. Yeah. The Wikipedia one. What is this though? Polish stuff? The main goal of BEAT is to design and implement an algorithm for solving an all relevant NP-complete class of problems using quantum computers effectively. Speed is better than quadratic, guaranteed by theory. Are they guaranteed by theory? We focus on the Hamiltonian cycle problem, but since there are known reductions between different problems inside the NP-complete class, we may say that we're working on all of them at the same time. So you're quantum working. Intelligent narozvoj. Who's behind these? Do I know? No. Never heard of any. Cool. Anyway, so this is it. This is it. This is it. This is it. Oh, sorry. Now the question. This will be really interesting, because that tells you, in a way, that tells you how the qubits entangle with each other, and so we should just kind of take these breakdown and make rules out of these, right? That's the way. Maybe that's the way forward. So in a way, it's like tensor networks, as I said. That oh man, I'm not having a good day today. That these. So if I have a qubit that is in the 0+1 state, and then I have another qubit that is in the 0 state, right? So that's my first, that's a system. So then I go here and say, okay, so cool, let's do a match. Now, yeah. So now, and note here the difference, right? So that's important because that's actually a change in the way that I was coding these. How did I call them? A linear, an LCOMB match. So we've got an LCOMB match here. So this means we've got to split the node, but we're not going to create two separate hyperedges yet, right? So we're going to have basically 0, 1. So we're going to split the node like this, right? I should use different notation for that probably, but whatever. So yeah, so that's what the lcom match does. It's just splitting the node into two nodes. And then I'm going to say, cool, so now now let's take a look and say, so thus running these rules. So how, here's the trick, right? So if a rule, so in this case, right, I've so in this case, if a rule effectively does a replacement, for every time a rule gets actually run, like this means that there's a match. It will create a new hyperedge, but of course you need to resolve for these, right? So that's the thing. So you run the rule. You kind of you run the rule only if there's like an actual non-lcom match, because I think that what you don't want to have lcom matches, right? So no, because that could even work for ccx gates. We'll see now. So if now I would kind of say, okay, now so you first of all you run this rules as many times as until you stop getting lcom matches. So I know it's really inefficient, but whatever. then then you basically go and say, because you could also just not write the rule, but like, yeah, kind of like do a sort of a swap, like you you go through all the sort of the nodes that you're trying to match, and every time that you have an outcome match, you do a split. And then you kind of do it again, and now you have a full match, right? And so now you're saying, cool, so now I have a full match. Now let me take a look at so the first is an outcome match, and now you have a full match, an F match, right? And now you go and say, now that I have a full match, now I'm gonna go and run sort of these other rules in here for these, right? But then every time that I actually have a match and I replace for something that is mathematically different, right? Let's see, it's just different for now. Let's deal with the face kickback a bit later. We can do this now, maybe soon. But so every time a rule hits and there's a replacement that leads into a different node, then that creates a hyperedge. So that then now you would have a 0, 0, and then you kind of would carve this out and say, well, the one's kind of like that, and then you're done. So what's created the separate edge is as a full match. Remember that we can't have two nodes. That's the thing, right? So we can't have at the end of running an operation, we can't have two nodes. I mean, we can, but then that would mean it's decoherent. But okay, so let's see how we'll enforce this, right? But like, just because this was split, then it means that I have to carve it out, because now I've gotten a match. Okay, so it will only actually create a hyperedge if it does a match on a split node. Yeah. So we'll actually create the hyperedge. Now, How would it work with the phase kickback? Can we make it work with the phase kickback without having to do a sort of a branch merging operation? So the phase kickback, let's try to follow the same logic. So to get a phase kickback, you do a you can do a let me check quickly with Quirk. This is so slow because this is just slow. Yeah. Man, this is just so slow. 21% CPU. Okay, so if I do these and then we are here, and now I do a Control X. Yeah, that is it. That's it, because here the blocks here was plus and it turns minus, right? So that there is a kickback. So we have a plus state and a minus state. So that's, we have a plus state, we have a minus state. Let's see what happens. Now we do a we have an LCOM match, so the same happens here. And now we do it again, and and have a full match. And so what we do here now with the full match is say, okay, so now let's replace the rules. But now, cool. So but now we have here an LCOM match, right? So this means I got to split the thing. So I split the thing, and that means that I end up with these, right? Now that's interesting. And now I have a, remember, what I want to do is I wanna end up not creating hyper edges here, because if I create hyper edges, I know this is not entangled. I know the outcome of these is not entangled at all. And I'd like to arrive that without having to create intermediate hyper edges. Because now what I'm saying is, now run these, right? Oh, God. We found a match. So what did I do before? So before, it's like I found a match and then I run these things. And the thing is, if I was finding a full match here, with a match on a mixed node here, then I was creating the hyper edge. But now the thing is, I found an LCOM match. So, but target qubit LCOM match, right? On control qubit, but target an LCOM match, and that's a different case now. Because and now I shouldn't create a hyper edge. I just basically do these. So I do the splitting, right? And now what? And now I would run these and then replace the 0 by a 1. The 0 by a 1. I'm missing something here, because if I replace the 0 simply, if I just simply go and now say cool, so now I can run. Now I can run this again because I've split the target qubit. So now I'll get full matches. So I get a full match here, right? And by the same logic, now that I get a full match here, I should create a hyper edge, right? But I don't want to do that, so I will just go ahead and replace these, and then this goes and it turns into these, right? So I'm what? I'm done. mm, I'm kind of done, but I'm kind of done, but it's not giving me the face kickback, right? Because I'd say I'm kind of done. So I'd say, okay, so first of all, I should be just writing nodes somewhere, and oh, so an lcom match splits nodes, then a full match on a non-split node on a non-local replacement on a full match whatever, yeah, he then creates a hyperedge, something like that. I'm gonna write these rules down. I think I'm onto something. I think I'm onto something. Full match. Like the thing is, here is a different case, right? So I did that, and then yeah, and now what, right? You might say I can just like plus and in a way minus, right? I wanted the minus to go up here because that's what the face kickback does. Because we know this doesn't entangle. We know this is the same, so we know this is the same like this one here, right? But it just has this extra kick, extra phase. That's what I'm missing. But I'll leave it here. But I think I'm onto something. So I like this. I like this new approach. I like this new approach of kind of like nesting the things like that. So saying like the non-local match replace. That making that distinction is something I was not doing in the original implementation. Because essentially that is what is missing. That is what I'm kind of missing from a yeah. To avoid the kind of full system like, hey, match is 0, 0 and replace with that, because that's not what I want to do. I want to do these, and I only want to create hyperedges in specific situations. And again, my guess will be to move to multi-qubit gates. Either there's a way you can do it like that still, or then you're just going to go through the decomposition, sort of the C naught decomposition of it, C naught plus unitaries, because then it basically means, yeah, and then you can kind of build like a big like non-local match replace for these, or a set of rules like that, and then that will act like that will be sort of a parallel, or that will act like a tensor network in a way of replacement rules. And yeah, but at least it should leave you. That's the goal. Is that I want these rules to end up like generating the right amount of hyperedges without you having to do some kind of resolving or refactoring, because that's the point. And I think that's the same point like with tensor networks, isn't it? That you don't end up with big things. You just kind of compress small things all the time. So you all the time have the smallest representation possible, and everything else stays connected. That's really what I want to do. Sort of it's nothing new really. It's just it helps me to think about these kind of things in different ways. And that is quite intuitive, because it's a bit of it's a bit more classical. It's like, if this is one, then do these. If this is no, 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 etc. Right? And then you end up with this kind of hypergraph that tells you, it kind of tells you how the qubits are entangled, which, yeah, essentially, I mean, I don't really know why will this be useful or not, but I mean, hopefully to study entanglement in a way. Let's see. I don't. I'm just. This is just really an exercise for me, for myself at the moment. And then, yeah, and then I want to go back to the whole quantum mechanics as well. But that specific problem bugs me a lot, so I really want to get it solved, and then kind of get my hands down coding on this while I do the other quantum mechanics stuff again. Cool. Let's see how the quality, how the stream will look like. I'm pretty happy with the way the whole Twitch Studio beta looks like, and it's fairly easy to use and to set up. So I might use that as well now, unless I would change the streaming platform, but I don't think I would. Cool. See you tomorrow.